Good morning, students. Today in this video, we will do a brief introduction to indefinite integral. Today we will do brief introduction to the indefinite integration. Let us start with a function. So suppose y is equal to fx is a function. Now we know that the derivative of this function y is equal to fx. This is f dash x. Okay. And in integration, in indefinite integration, we find the function whose derivative is given to us. So indefinite integration is also, we can say this is antiderivative. Derivative. So uh, antiderivative. It's antiderivative. In derivative, we find let us first define indefinite integration. So this is the process of finding the function whose derivative is given. Okay, that is, suppose if we are given the derivative of a function f dash x, then process of finding the function fx is called integration. Okay, this is called integration. Let us understand this by an example. Suppose we are given the function fx is equal to x square. Okay, its derivative is given by y is equal to fx is equal to x square. Its derivative is given by 2x. You know the derivative of fx is equal to x square is 2x. Now, integration of 2x, okay, means the process of finding this function x square. This is called integration. So integral of 2x is x square. If this function was y is equal to x square plus say 3, then derivative of this function dy by dx is equal to 2x. And now if we are integrating this function 2x, then its function y means the derivative, if the derivative is 2x, then the function x square plus 3 whose derivative is 2x will be written like this, x square plus 3. So in general, if we are given the function 2x, then its integral will be written as x square plus the arbitrary constant c. We have to write this arbitrary constant c. Uh, Let us understand this why we always have to write this arbitrary constant c when we are writing the integral of any function. We will do it by this example itself. Suppose we are given the function y is equal to say x square, y is equal to x square plus 1, y is equal to x square plus 2, or y is equal to say x square minus 1. In all these cases, the derivative of these functions is 2x. Yeah, either if you have taken the function y is equal to x square or this or this or this, the derivative of any of these function, we can have many infinite functions with any arbitrary constant. Here the constant is 0, 1, 2, minus 1, or any constant. The derivative is 2x. Now let us draw the graph of these functions. This is a parabola. This is a parabola, y-axis. This is the origin O. And first we will draw the graph of y is equal to x square. So this is the graph of y is equal to x square. Then say this is 1. Then graph of y is equal to x square plus 1 is something like this. Okay. Say y is equal to x square plus 2. This is also a parabola whose vertex is at 2. The vertex here is at 1. The vertex here is at 0. The graph of this y is equal to x square minus 1. The vertex of this parabola is at y is equal to minus 1. Okay. Now let us take this point x is equal to 1 on the x-axis and see what is and let us draw tangents at these points. Okay, at x is equal to 1 on this curve, at x is equal to 1 on the second curve, means y is equal to x square plus 1. Then at x is equal to 1, we are drawing a tangent. Okay, at x is equal to 1, and on this graph x square minus 1, we are drawing the tangent at x is equal to 1. So on all these graphs, we have drawn the tangents at x is equal to 1. Now, when we find derivative of any of these functions, we are actually finding the slope of the tangents drawn to these curves. And here in this particular case, at x is equal to 1, the slope of the tangent will be 2. Means these tangents that we have drawn on these different curves at x is equal to 1 have slope 2. The slope of this tangent is 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 2. So this we have taken a particular case. Okay. Now the curve, yeah, you can say if we are given the slope of the tangents to all these curves is same. So this was a particular case at x is equal to 1. So in general, if you are given 2x as the slope of the tangent to different curves, now by integrating this function 2x, we are finding the curve to which this slope of the tangent we have found, or you can say we are finding the curve whose derivative is given to us. So this was the geometrical meaning of the integration. This was geometrical meaning of integration. Yeah, this is the geometrical meaning of integration. Uh, Let us take some functions whose derivative we know, like suppose we are given the function y is equal to x raised to the power n plus 1 upon n plus 1. Okay. Now derivative, we know that derivative of this function is x raised to the power n plus 1. So its derivative will be n plus 1. Let us write it again. Okay. dy by dx, derivative of this function, this is equal to n plus 1 x raised to the power n plus 1 minus 1. So you will get x raised to the power n upon n plus 1. So integration of this function, integral of this is equal to x raised to the power n. Therefore, integral of x raised to the power n will be equal to x raised to the power n plus 1 upon n plus 1. And of course, plus constant of integration also we have to write, because um, we can have many functions whose derivative is x raised to the power n. So what actually we are finding? We are finding different uh, functions whose derivative are known to us. Again, we know that derivative, if the function is y is equal to sine x, then derivative of sine x is cos x. Cos x. Therefore, integral of cos x dx, this is equal to sine x. Then if the function is cos x, its derivative is sine x, minus sine x. So if the function is minus cos x, its derivative will be plus sine x, and hence integral of sine x will be minus cos x plus constant of integration. Constant of integration we have to write everywhere where we are finding the where we are doing the integration of different functions. This we always have to write. Then we know that derivative of the trigonometric function tan x, this is equal to sec square x. Then it's the integral of sec square x will be equal to tan x plus c. Again, derivative of cot x, this is equal to minus cosec square x. Therefore, integral of, or you can say the derivative of minus cot x is cosec square x. Therefore, integral of cosec square x is minus cot x plus c. We have done how many trigonometric functions? 1, 2, 3, 4. Now, the next is derivative of sec x. The derivative of sec x is sec x tan x. Hence, integral of sec x tan x dx is equal to sec x plus c. Similarly, derivative of uh, cosec x. Cosec x, the derivative of cosec x is minus cot x cosec x, or derivative of minus cosec x is cot x plus cosec x. Therefore, integral of cot x cosec x is equal to minus cot x, sorry, minus cosec x, minus cosec x plus c. Then the first function that we did was integral of x raised to the power n. Yes. Now we know that derivative of the function x, this is equal to 1. Therefore, integral of dx, this is equal to x plus c. Okay. Then derivative of e raised to the power x, this is e raised to the power x. Therefore, integral of e raised to the power x dx is equal to e raised to the power x plus c. Similarly, derivative of log x, this is equal to 1 upon x. Therefore, integral of 1 upon x dx, this is equal to log x plus c. Now let us do the yes, derivative of a raised to the power x. This is equal to a to the power x log a. Okay, or derivative of uh, a to the power x upon log a. This will be equal to a to the power x. Okay, derivative of a to the power x is a to the power x log a. Therefore, derivative of a to the power x upon log a will be a to the power x, and hence integral of a to the power x dx will be equal to a to the power x upon log a plus the constant of integration. These are the functions whose derivative are known to us. You know, these are the derivatives of these functions. So the integral of these functions we can write. The integral of these functions we can write. Now, similarly, we know that derivative of sine inverse x, derivative of sine inverse x is 1 upon square root of 1 minus x square. Therefore, integral of 1 upon square root of 1 minus x square dx. This is equal to sine inverse x plus c. Then derivative of tan inverse x, this is equal to 1 upon 1 plus x square. Therefore, integral of 1 upon 1 plus x square dx is tan inverse x plus c. Derivative of um, sec inverse x. This is equal to 1 upon x under root x square minus 1. Therefore, integral of 1 upon x under root x square minus 1 dx will be equal to sec inverse x plus c. These were the few functions whose derivatives, these were the functions whose derivative we know, and hence we can integrate these functions to find the function. Okay, whose derivative are these functions. Now, uh, uh, let us see, in these examples that we have in this part, we have done the derivative of the integral of x to the power n, then integral of sine x, cos x, then there were few more functions like sec x, tan x, okay, then minus cosec square x, and so on. Here we haven't done the derivation, the integral of tan x. Okay, tan x integral of this function we haven't done till now. Then integral of cot x also we don't know. Then integral of cosec x also we don't know. Then integral of uh, sec x also we don't know. Okay, so now in next, let us see how to find the integral of all these functions. Now, first of all, uh, how to wait. Now in this part we are going to find the integral of these functions. For that, first we have to see the integration by parts. Okay, till now we have done the integration of different functions by simply observing the function and writing its integration. Now in this part we are going to find the integral by substitution method. Okay, how we suppose we are given any function like fx dx. We have to find the integral of this function. We don't know, we don't know directly by observing this function that what will be its integral. So what we do here, we substitute x as some function of t. We substitute this function as some function of t, say x is equal to gt, and then differentiate it with respect to t. You will get g dash t into dt, and we write this function which is in terms of x. We substitute t here in this function, so it will become f of gt into g dash t dt. In this way, sometimes the functions become very easy, and simply by observing this function we can write its integral. Like uh, uh, the function suppose we are given is say fx is equal to 10x. We want to find the integral of this function. That is, we want to find integral of 10x dx. Okay, we don't know, we directly don't know the function whose derivative is 10x. So we do this integral by substitution method, and we can write this function 10x like this: sin x upon cos x dx. We substitute cos x as some function t and differentiate this function with respect to x. So we'll get minus sin x, okay, into dx. Or you can write this as minus dt is equal to sin x dx. So this function, or this function sin x upon cos x dx, after substitution will be written like this. In place of sin x dx, you will write minus dt upon t. This is equal to minus log of t plus constant of integration. Now our t is equal to cos x. So this is minus log of cos x plus c. Or you can write this as log of cos x raised to the power minus 1. This is the property of logarithmic functions that we are using now. Log of cos x raised to the power minus 1, or log of 1 upon cos x plus c. All this is equal to log of sec x plus constant of integration. So this is the derivative, sorry, uh, this is the integral of 10x. Means if you are differentiating this function log of sec x, you will get 10x, and hence the integral of this function 10x will be log of sec x plus c. Uh, Similarly, we can find the integral of cot x dx. This also we will do by substitution method. We know that cot x is equal to cos x upon sin x dx. This is equal to sin x. Let us substitute sin x as equal to t and differentiate this function with respect to x. So this is cos x or dt is equal to cos x dx. Therefore, now this function cot x, which was equal to cos x upon sin x, you can write this function as, in place of cos x dx, you will write dt upon sin x is equal to t. So this is dt upon t, or after integrating, now we know that integral of 1 upon t is log t plus c. This is equal to log of sin x plus c. Yes, so if you differentiate log of sin x, you will get cot x, and hence integral of cot x will be log of sin x. Now we will find the integral of sec x dx. Sec x, because we don't know, we have done till now the derivative of integral of in trigonometric functions, we have done integral of sin x, cos x, and tan x. Now we are doing the integral of sec x. So sec x can be written as sec x into sec x plus tan x upon sec x plus tan x dx. This is equal to integral of sec square x plus sec x tan x upon sec x plus tan x. Here we can substitute sec x plus tan x as t, because derivative of sec x is sec x tan x and derivative of tan x is sec square x. So here you substitute t is equal to sec x plus tan x, and differentiate this t with respect to x, you will get sec x tan x plus sec square x into dx. So this function, this is in terms of t, after substitution will become dt upon t, which is equal to, again we know that integral of 1 upon t is log of t plus c. So this is equal to log of t. We have assumed it to be equal to sec x plus tan x plus c. Now we have written here the absolute value of sec x plus tan x, because log of negative number is not defined. So we take the absolute value of this expression sec x plus tan x, means this value has always to be positive value. So if we are going to differentiate this function, the derivative of this function will be sec x, and hence the integral of sec x will be log of sec x plus tan x. Now, one last trigonometric function, that is uh, cosec x is left, whose derivative we are going to, sorry, whose integral we are going to find. Cosec x. Now we are going to find the integral of cosec x. So for cosec x, let us write this as equal to integral of cosec x into cosec x plus cot x. You multiply and divide the numerator and denominator by cosec x plus cot x upon cosec x plus cot x dx. Okay. Let us expand this expression, so that will be cosec square x plus cosec x cot x divided by cosec x plus cot x dx. Okay, here let us substitute cosec x plus cot x as equal to t. So on differentiating this function with respect to x, you will get the derivative of cosec x is minus cot x cosec x, and derivative of cot x is minus cosec square x dx. Let us take these two minus common outside. So this will become plus, or let us take this minus on this side. So minus dt will be equal to cot x cosec x plus cosec square x dx. So after substitution, you can write this function as equal to integral of minus integral of minus dt upon t. This is equal to minus log of t plus c. This is log of 1 upon t, and t is equal to cosec x plus cot x plus constant of integration. Let us multiply the numerator and denominator of this function, this expression, by cosec x minus cot x. So you will get log of cosec x minus cot x upon cosec square x minus cot square x plus constant of integration. This is equal to, now cosec square x minus cot square x is 1. So you will get log of cosec x minus cot x plus constant of integration. This again we are writing in absolute value because negative of logarithmic function is not defined. So students, till now we have done the very basic part, yeah, very basic introduction of indefinite integration. In indefinite integration, we are finding the function whose derivative is known to us. Thank you.